Engineering Eng.
Hello friends. With this lesson, I would like to introduce a course that can be considered a continuation of the electromagnetic theory course we call wave theory. The most important thing in this lesson, friends, is Maxwell's equations. Because everything is built upon this. For example, in the electromagnetic theory course, we dealt with static fields by considering the partial derivative with respect to time, here denoted as del over del t, as essentially zero, and worked separately with the electric field and the magnetic field. But here, for the wave to form, the electromagnetic and magnetic fields need to be together. Now, if you like, let's focus on Maxwell's equations. We have four fundamental Maxwell equations. All of these are important. In fact, 3 out of 4 are more significant. For example, the third equation we use as Gauss's law, and the fourth equation also come from here, friends. So this is actually one of Maxwell's equations. Let's explain the logic of Maxwell. First of all, what do E, B, H, and D mean here? Let's talk a bit about these if you like. First of all, E here is the electric field, which you probably know a bit about. Its unit is volts per meter, and we were more concerned with the intensity of the electric field. We also focused a lot on this in the electromagnetic course. This is considered an electromagnetic course, and we can say it's essentially the same thing. We will focus more on the wave properties in this course. Later on, H refers to the magnetic field intensity, which is referred to as intensity in English. Furthermore, D is obtained by multiplying epsilon with E. Similarly, the relationship of B with H is related to what we call permeability, which is the magnetic field permeability constant, obtained by multiplying the magnetic field intensity. This value is related to the magnetic flux density we refer to. The first two are related to intensity, while the last two are related to density. We also have current density when our current density is current itself that falls within a specific square meter or volume. I will write these down shortly, but first, let's try to understand the logic of an event from the first and second equations. Now, friends, there is always a rule. In the logic of the event in Maxwell's equations, normally when writing an equation like x equals ax plus b, y is x, generally here. These are the result of ax plus b, meaning x takes something in and ultimately gives us the equation ax plus b. But here it's the opposite. It's not cause and effect, but effect and reason, friends. In Maxwell's equations, the right side always gives us the reason for the event, and the resulting thing is on the left side of the equation. Now let me try to explain what I mean by this. For example, you can think of B and H in the same way here, because the only difference between B and H is that we can reach B by multiplying H by the permeability constant. So we can think of B as somewhat like H. In other words, we can consider it as a magnetic field, which is not very different. Now, what does the first equation tell us about the magnetic field? First of all, why is it called the Maxwell-Faraday equation? Let's talk about that first. You can remember the Maxwell-Faraday equation like this. What was the electric field, friends? We used to say kq divided by d. We reached it through q, which means charge. Let's write the charges here, for example. What is equal to E, for example, kq divided by d2. Here, the charge q, what is the unit of charge? Faraday. That's why the electric field is related to Faraday, which is why the first equation is called the Maxwell-Faraday equation. Similarly, what was the magnetic field, friends? If I induce a certain wire, for example, if I wrap it like this, and if I apply a current to this wire, a magnetic field would be induced inside it, if you remember. So, who is related to the current? It is Ampere. Who is associated with Ampere? The magnetic field. Therefore, what we call H here also appears as the Maxwell-Ampere equation. Friends, now let's examine this result relationship for some reason and create an electromagnetic wave. Now, in the electromagnetic wave, it first tells me, look at this part, it says if you have a magnetic field. If you have a magnetic field, and this magnetic field changes over time, you know why an AC signal is drawn like this, friends. The reason an AC signal is drawn like this is that it has a continuously changing amplitude on the time axis. This part is the amplitude function. So this sign, that is the change in the sinusoidal sign, this change here is provided by differentiation. Now it tells me that if this magnetic field changes over time, as a result an electric field is formed, friends. I have now changed a magnetic field like this over time. Let this be the magnetic field, friends. it says that afterwards it creates an electric field around it in a perpendicular manner. It created an electric field like this. Then it says to me, now the electric field has formed. Remember that D was related to E. Because I mentioned its relationship here a moment ago, what was it, D and E? The direct relationship of the electric field is with epsilon, which is the permittivity, meaning the intensity of the medium given to the electric field, multiplied by what we call the dielectric constant E. Epsilon tells us that D and E are directly related, so I can think of E like D. Later, this D was formed here, meaning the electric field was created. It says that if this also changes with time, as a result of this I was saying why it occurs, meaning the right side is the cause, and the left side is the result. Normally in an equation the left side is the cause, and the right side is the result, while in Maxwell's equations the right side is the cause, and the left side is the result. We must not forget this. Then it says that in the case where this occurs, meaning if this time-dependent change continues, as a result, a magnetic field will form around it, friends. A hash was formed around it again. Then, if this magnetic field is formed again, and this time-dependent change continues, it creates this again like this. This creates this, this creates this, this creates this, this creates this. As this formation continues, it is a kind of electromagnetic wave propagation, and the electromagnetic wave is formed like this, friends. The logic of the event comes from here. Then when we examine the second equation, I see J here, and I see sigma. These mean current density. Here, J, which refers to a certain current falling on a specific square meter or cubic meter. We name this certain I0 current as J. Friends, if it is square meters, we denote it with S, and if it is cubic meters, we denote it with V, meaning we represent it volumetrically. After expressing this in this way, friends, we then move on to our third and fourth equations. By the way, sigma E is here. Sigma E is also a kind of current density, because it must have the same unit in any equation. If this is current density, then this is also a current density. And as you know, sigma here is the conductivity coefficient. What was the English term for conductivity? It is conductivity. We can say this is a current due to the conductivity of the medium, the product of conductivity and the electric field, which you know has a unit. The unit of conductivity is Siemens per meter, or 1/10 meters. Let's write this down. I will perform an operation related to units shortly. Let this be a preparation for that. Later on, the Gauss's law, which is the most used by you in our first electromagnetic course, actually comes from Maxwell as well. This equation is quite familiar. You may have seen it. So what does this mean for us? It expresses the following. It says that if there is a certain charge density in a specific region, the electric field and magnetic field lines entering here pass into the opposite area with different magnitudes. In other words, let's express it this way. If the medium has a certain charge density, it somewhat represents the Nabla operator, which I have explained in electromagnetic classes. If you haven't listened to those classes, I recommend watching them again. In terms of derivative, it represents a kind of differentiation change. It says that if there is a charge there, meaning if 2 units have entered here, it will continue with a different unit, like 3 or 4 units. So if there is a charge density resulting from it that is different from 0, it means that it will create a change in the linear lines here, indicating a change. We can also think that this has occurred as a result of that. At the same time, it establishes a linearity. If you obtain a result that is different from 0 when you apply any Nabla operator with the dot product to any vector A, it also represents that these lines are linear, meaning they do not return to the starting point. I explained this in the electromagnetics classes from a year ago. Our last equation expresses that the divergence of P, which we refer to as the magnetic field, is always cyclical. Notice that I mentioned earlier that if it is not 0, it is linear. But be aware that here you will always get a result of 0. Regarding the maximum magnetic field, if you write nu H instead of B for the magnetic flux density here, it simplifies to 0, and actually divergence H equals, this is also 0. Therefore, the result from the divergence here tells us that Our magnetic field lines are cyclical, meaning they return to the source they originated from. Friends, after stating this, we mentioned our units a moment ago. The unit of electric field is volts per meter, and the unit of magnetic field is amperes per meter. The unit of electric flux density here is coulombs per square meter. The unit of magnetic flux density here is also Webers per square meter. Now, if you like, let's see how some important formulas that we know are derived from the general formulas. The most basic formulas actually come from Maxwell, friends. Now let's write these units if you want. For example, let's perform this operation. For example, let's take the unit of D. I'm writing coulombs per square meter here. Look, I wrote the square meter as meter times meter. By the way, we need to write the unit of epsilon. The unit of epsilon is farads per meter, friends. Let's write it like this. And in the electric field, volt per meter, I wrote it down here again. Look, I wrote it from the top here. Now look, if the meters cancel out here, friends, if the meters cancel out here as well, when we say coulomb, what comes to our mind, friends? Charge, right? We generally use Q as charge. And when we think of capacitors, we use C for capacitance. And when we take volt as volt, the most basic formula we know, Q equals C times V, actually comes from here. Friends, I wanted to show you this. Later, let's also do this operation for B equals Nu times H. I wrote B's unit as Weber per square meter, again writing it as meter times meter. The unit of Nu, friends, is 1 over Henry per meter, meaning we have an inductor like this in the medium. We express this as L, this inductor. When we apply a current here, a magnetic field is formed, as you know. How do we always express L here? We express it in Henry, and as Henry per given meter. This is the unit of Nu. We also wrote the unit of H here. Look, Ampere per meter. I'm writing this down too. Later, if the meters here cancel out, Weber, friends, was the unit of flux. Therefore, we would also show the flux like this. You might remember it from high school. When we say Henry, what comes to our mind? And as current, we generally use I well, the most basic flux formula. F, actually capital, F equals L times I, comes from here, friends. In another fundamental formula, I write here J equals SE. Well, I use this to equal the units. So this is also current density. This is also current density. As you know, in the second equation, look here, there is current density. This means their units must be the same. So, I say that the unit of this is the same as the unit of that, and let's apply this operation to this as well. Then I say that the equality of the units must be ensured, and I ask, since this current density is what our current density means, friends, if we were to write the unit for a specific current. Let's correct it like this. What is the unit of current? Friends, we are writing the units here, and the unit is amperes per square meter, or amperes per certain square meter or meter. Later, the unit of conductivity is Siemens per meter. What was the unit of the electric field here? I wrote it a moment ago. Volts per meter. Now, if the meters here cancel out, friends, I am using this instead of amperes. We generally express amperes as I, just like here. Later, C means 1 over ohm. And if we gather this equation here, friends, what do we use for R? We express resistance with R, right? If I take it as R, and if I write it as I times R, here is the most basic and equivalent I times R. And again, we reach this by ensuring the equality of the units from Maxwell. Friends, yes, friends, now I am thinking about what else I can provide you with as information. Now we have time-independent equations and an equation called the Helmholtz equation, which is also an equation that can be obtained from the curl operation of Maxwell's equations. Here, U represents any field for us. We will use this more often anyway, By using this U, we will try to reach all other fields with the given electric field and magnetic field components by working with the Helmholtz equation. This is also a very important equation for us. Here, k is the wave number, and the most general formula is 2 pi divided by lambda. If you recall, 2 pi divided by lambda is something you know from high school. For example, omega equals what? Meaning angular velocity is 2 pi divided by the period, if you remember. Since frequency is equal to 1 divided by the period here, it is somewhat equal to 2 pif. Therefore, if I multiply both sides by f, it turns into 2 pf, which is the omega we know. In lambda times f, the most basic thing we know is that lambda divided by t equals the wavelength, and the part that gives the speed of light. If you remember, this way, we reach c. Lambda times f gives c, as you know. Therefore, if I write c instead of lambda times f here, and omega instead of 2p divided by f, k is also equal to omega divided by c. If you know that c is equal to 1 divided by the square root of epsilon times nu0, meaning the square root of the product of permittivity and permeability, if you substitute this in, the law becomes omega times the square root of epsilon times nu0, where the zeros represent the space. You can also refer to epsilon n and nu n here. These can vary for any medium. In this way, we can see the important coefficients for us here. Finally, after the fields are given here, we use the time-independent Maxwell equations, which are the most commonly used, for converting them into each other. Here we have del cross e to the power of j omega nu, and we want to isolate her, so we would like to keep this del cross on this side so that her remains alone here. Let's perform the del cross operation here and try to find the equations of the other fields. The same thing applies here as well. Del cross A to the power of y omega epsilon is equal to the electric field. If we isolate the electric field from here, we get 1 over epsilon, which is the part where we will perform the determinant operation, meaning the cross operation. I have also explained how the cross operation is done in electromagnetic courses, and I recommend watching it. By performing the operation here, we reach the electric field. Friends, basically, it is sufficient for us to know these for now. Of course, there are many more things. For now, I have tried to explain what comes to my mind for the introduction. I have written them down here. The first 2 of the 4 fundamental equations are generally the ones we deal with the most, and we will be working more with the Helmholtz equation here. This Helmholtz equation is also a general formula derived from Maxwell's equations. Later on, we will also try to reach the desired fields using the time-independent Maxwell equations. Let's see how successful we will be. I hope to see you in upcoming videos. For now, goodbye, friends.